go over the math behind PCA, and then Alan will talk about how you can use PCA in scikit-learn for modeling purposes. Okay, go for it.
All right. As Serge mentioned, we'll start with decision trees. I think people generally didn't have too many issues with like actually fitting a decision tree and like fitting a random forest, because those functions were pretty similar to how you would do it in like with linear regression and logistic regression. So for this part, I think I'm just gonna pretty much just go over like entropy, weighted entropy, and how like you would actually fit a decision tree if you had to like do it from scratch. So first, this MVA data set that you've seen like a bunch of times. And then these are the two like functions that like, I mean, not functions, but like two formulas that you kind of have to remember from the decision trees lecture. There are probably other formulas, but these are like the two main ones. First thing is like the entropy. The second thing is the weighted entropy. So the entropy, as you may recall, is the negative sum over all the classes of the probability of that class times log base 2 of the probability of the class. So an important point is this is a log base 2. It's not like a ln or like a log base 10 or something. You might see like ln in some places, but for the purposes of this class, we'll use log base 2 for entropy. And weighted entropy is pretty much just a weighted average of the entropy based off of your split. So for this class, we don't really talk about splitting into like 3 different branches. We just talk about splitting into like 2 branches. So this is the way you would calculate like the weighted entropy if you wanted to split into 2 branches. So N1 is the number of samples in the left branch or left node. N2 is the number of samples in the right node. And what you can do is take N1 times the entropy of your left node plus N2 times the entropy of your right node and divide by the sum of the sum of the samples, the total number of samples. So that'll like weight the left node and right node accordingly, depending on how many samples were in that node. So these are the functions you implemented in Lab 11. It's pretty much the same thing. The entropy function and the weighted metrics function, which you can like plug in entropy here. So first, a quick overview or recap of entropy. So what is the entropy if I just have a bunch of labels, but they're all the same? So what is the output of this? 0. Yeah, so this is 0. So if I just have the same label, this is just -1 log base 2 of 1. Log base 2 of 1 is 0, so this is just 0. So what happens if I have 1 of one thing and 1 of another thing? What is the entropy in that case? Okay, I have some 1s. Yeah, so it's a 1. The way you would calculate that is you have negative, so PC is 1/2 for C here and 1/2 for SG, so it's negative 0.5 times log base 2 of 0.5 minus 0.5 times log base 2 of 0.5. So that's 1. Okay, and then, so this is like if I had 1 center and 1 shooting guard, but what if I had 10 centers and 10 shooting guards? What is the entropy in that case? Is it the same or would it change from this?
Would the entropy be 10?
Yeah, would it be 10? Would it be 110? Would it still be 1? Would it be 0? Yeah, so it's also 1 because like someone mentioned in the chat, PC is still the same. So the probability of center here is 10 out of 20, which is still 1/2. and the probability of a shooting guard is 10 out of 20, which is still 1/2. So this is the same as this basically, except I just have 10 more copies of everything. So this like calculation you can still use for this. Okay, what happens if I have one of each of the three, or each of three things? What is the entropy in that case? It's okay if you don't simplify your answer. Yeah, basically that. So the probability of one of these is 1/3, and I have 3 of them, so I sum that 3 times. So negative 0.33 log base 2 of 0.33, and then I have 3 of those, so it's gonna be like slightly off, but because I'm using 0.33 and not 0.333333. But yeah, this is the same as np.log base 2 of 3. It's slightly off because I'm using 0.33 here instead of 1/3. One thing to note is if you're not comfortable with like log rules, one thing to recall is if I do np.log base 2 of 1/3 or negative of that, that's the same thing as np.log base 2 of 3, because what the log rule says is I can move this negative inside the logarithm, but invert what's inside the logarithm, basically. Okay, any questions on entropy before we get into weighted entropy? So we didn't really discuss the theory of entropy in that much detail, but you can see like if the entropy of something that like you can kind of think of the entropy as like a surprise factor. The entropy of something which it's just a bunch of the same things over and over again, that's 0. But if you have like a bit more like disorder, like a bit more randomness here, we would have more entropy. And when we had like 3 labels, it would have had more entropy than if it had 2 labels. And like it was split evenly. Okay, so why do we use weighted entropy? Why don't we just use like something like average entropy? Why can't we just do S of X plus S of Y over 2? So this is just a crude example where I have 10 centers and 10 shooting guards, and I want to do some sort of split. So if I just used entropy, like if I just used the average entropy, just added the 2 and divided by 2, I'm comparing 2 splits here. So I have one split, which I just split one center on one side and everything else on the other side. So the average entropy in that case is 0.499. But on the other hand, I could split 4 centers and 1 shooting guard on one side and 6 centers and 9 shooting guards on the other side. And we'll see that average entropy is much higher. But you might not like want this split over this split, because what we can do if this was always better is I can just split one center off every single time, or sorry, this is actually, let's see, 9 and 10, but it doesn't change the entropy. What I can do is split this like one center off, not like 10 times. Like then like my decision tree would have like depth 10, but that's like, as you might remember, like decision trees are very prone to overfitting, and if I just make a decision tree that's like this tall, that's not necessarily a good thing. So this is why we might want to use something like weighted entropy, because although this split, like this left node, isn't as like good in terms of entry on that node as this node, because this has 4 centers and 1 shooting guard. This only has 1 center, so this has entropy 0. This has entropy that's something that's greater than 0. But because I'm splitting like more nodes here on one side, you generally can think of this as a better split than this. And you can see that when I do the weighted entropy calculation, this split is better than this split. So that's like one reason why you'd use like weighted entropy as your like kind of loss function where you're determining a split. All right. Any questions on weighted entropy before I?
So we use weighted entropy to prevent our tree to get too deep.
Sorry, what was that?
So we use weighted entropy loss to prevent our decision tree to get too big.
Yeah, that's one way you can think about it is, I wouldn't say that's like the direct reason, but using weighted entropy is a good metric for decision trees because you can avoid situations like this where if I just split one node at a, like if I just split off one label at a time, it would just give me the best result every time. So in that sense, you can think of that. But I would say like the direct, it's not like directly related to making your decision tree tall, if that makes sense. Like if you want to try to avoid making your decision tree tall, you should try other things such as pruning, or like if you run into a node where there's like only like 5 samples left, then maybe we just stop there. There are other ways you can like you can do to try to stop making your decision tree tall. Using weighted entropy is kind of not directly related to that, if that makes sense. Okay, on to fitting decision trees. So we didn't really go over like the very, we kind of went over fitting decision trees in a high level, not really in detail. So how you can fit decision tree is basically you start with all your labels. So I have all of MBA here, like 708 rows and 30 columns. Let's do that, so it's not that big. So you have all your labels. This here we're trying to predict the position. So I think there are 5 positions. So we're trying to predict one of those 5 positions. So what you do starting off is at your root node, you have all your labels. You have like all these features that you want to use, and you want to try to find the split that minimizes the weighted entropy after you split. So what you can do, and this is essentially the process, is just try a random feature or like the best feature. Find like a split value you can use. So here I'm using age and 30. And then like pretty much try every single combination of split, like the feature and the split value as you can, and just try to find the best one. So here I'm trying age 30. Here I'm trying age 25. Here I'm trying field goal 5. Here I'm trying FGA 5. I'm just trying to find the one that minimizes the weighted entropy. So there are a lot, because there are like a million features here, that like there are a lot of ways you can do splits. So I just did 4 for example, and this one gave me the lowest weighted entropy. So I'm just gonna pretend that this one was the best. But in reality, you would like actually try every single feature and every possible split until you get one that minimizes the weighted entropy. So I'm just gonna assume that MBA age greater than or equal to 25 and less than 25 is the best split. So I split this into the left and the right. So if you look at left, it only has 425 things now. If you look at right, it has like the rest, so 283. So we started off with like all 700 records, but now we only have 425 on our left branch and 283 on our right branch. So now from here, what you can do is basically just go through that process over again, except now you're only focusing on the records that you have left. So here I'm just using FG3 But what you would do is like basically try every single combination again here. So I could try like FG2 here as well. And then like FGA5 or whatever. And I just try all those combinations until I find the best one. And then I split this like recursively. So I would pretty much do this process again, except only with the data on the left node. And similarly, this would be the same as like the right node. I would just repeat the process as I did for the root node, but for the right node, where I'm only focusing on the data on the right node. And I just continue doing that until like I have a node that only has centers or something, or a node that only has like one of the 5 things, because then I can't split it anymore. There's also like the edge case where like if I had all the same features and they're a center, but there's another player had all the same features but was a power forward or something. In that case, we can't split it either because like they have the same features but different labels. So we can't. There's nothing we can do. But okay, any last questions on decision trees before we move to Serge's part? All right.
I have a question.
Yeah.
You mentioned the decision tree, the algorithm we show is very recursive.
Yeah.
So is it generally slower than other methods?
Slower than other methods. I think there's usually only one way to fit a decision tree, as far like one main way, and this is like the recursive way is basically the one main way you would do it. But there are methods where you can, like the way I was saying, like try all the features and try all the splits. That seems really slow, but there are ways that you can do there are things you can do to make that faster. But those are like outside of the scope of this class. Talk about pruning. Is there a best way to figure out where to prune? Is there a best way to figure out where to prune is the question. I would say there's not an easy way to figure out exactly where to prune or how to prune. But what you can do is look at your cross-validation error and like prune a branch of the tree, check if the cross-validation error decreases. If it does, then we can prune that branch, or cross-validation accuracy. Sorry. If the cross-validation accuracy decreases, then maybe we don't want to prune that branch. But if the cross-validation accuracy increases after pruning that branch, then maybe we want to actually prune that branch, because then that could be a sign that we're overfitting. Great question, by the way. All right, I'm going to move on to Serge because he has a lot to talk about. Feel free to ask any more questions in the chat, though.
Cool. All right. Get the chat open here. All right. So I want to talk about the math behind PCA, maybe remotivate it, because it seems like on the week 7 survey, a lot of students weren't really sure how exactly the SVD is used and things like that. But I will try and go relatively quickly because most of this should be review. But at any point, please stop me if you have any questions. And of course, all of this will be posted. So consider the setting where we have some design matrix X that has, I don't know, 50 or 500 or 500 million columns, right? And maybe we want to visualize some of the features in our matrix, or we want to fit a linear regression model, but we don't really want to deal with the computational complexity of having 500 million features or columns. So one naive way that we could reduce the dimensionality of our design matrix X is to just ignore a bunch of our features, right? So I have some random design matrix here, or rather a structure of a design matrix where the features are like age, height, length. I'm not really sure this is the length of it, probably should be weight. GPA, income, number of siblings, whatever, just random things I came up with. And suppose we just want to have a visualization or a linear model that only has 2 features. Well, one thing we could do is look at this and say, hey, well, depending on what I'm trying to predict, maybe only these two features are important. Or maybe just choosing, I don't know, these two features will give me an interesting scatter plot or an interesting linear model. Okay, so you could just manually pick some features on your own. But if you were to do that, that would throw away a lot of the important information in our sort of design matrix that isn't in those two columns that we selected. And so all principal components are linear combinations of all of the features in our design matrix. And our goal with PCA is to find the best possible linear combinations of our original columns. Okay, so principal components are linear combinations of all features in our design matrix. And what we want is our principal components to capture as much variation or as much variance in our original data set as possible. I want to capture now this is more of a like philosophical perspective, but information is variation. Variation is information, right? Like if you have a column that is the same number for everybody, that's not really telling you anything about, you know, their behavior or something, right? So we want to maximize as much, and we want to maximize variance essentially in our principal components, and that's all they are. And so we'll take a brief diversion to the singular value decomposition, look at the dimensions of the resulting matrices, and then talk about how we use the singular value decomposition for principal component analysis. So the singular value decomposition, probably was no need to write that full name out, but anyways. So the SVD takes our design matrix X that we assume is mean centered. And in lab 13 and in homework 8, whenever you call the singular value decomposition in NumPy, you always assumed that your design matrix, you know, you sort of subtract the column means from it. I won't talk exactly about why we need to do that right now, just because to give an explanation that I would be happy with would take up more time than we really have here, but we can sort of talk about that after, and I can write it in the notes if you're interested. But anyways, we assume our design matrix is mean-centered. The singular value decomposition takes our matrix and writes it as a product of these three other matrices, U, sigma, and V transpose. Okay, how it comes up with these matrices, for our purposes, who cares? It just does it, okay? And we are going to work with these sort of returned matrices without worrying about how we came up with them. Okay, so what are these matrices? Well, first let's look at the dimensions. Let's just assume for now that X, our design matrix, is n rows and n rows and d columns, okay, or d features. I know in lecture we typically said we have p features or p+1 features, but sort of when talking about matrices on their own outside of the data context, you typically see n by d a little more often. But anyways, cool. The result of the singular value decomposition is this matrix U that also has dimensions n by d, this matrix sigma, which has dimensions d by d, and this matrix V transpose, which has dimensions also d by d. And so you can see when you perform the multiplication of U, sigma, and V transpose, these inner dimensions cancel out. And so the result of U times sigma is a matrix with dimensions n by d. And when we multiply that by V transpose, these inner dimensions also collapse, and the result is also a matrix with dimensions n by d. So, okay, great. We know what the dimensions of U, sigma, and Vt are. Who cares? What can we do with it? Well, let's look at it. So U and V both have this property that the columns of that their columns are all orthonormal to one another. What does that mean? Well, let's write U as, consisting a set of column vectors. Question, what should the subscript I put here be? How many column vectors make up U? D, good, because we said that U has D columns. Great. V also has D columns. V1, V2, VD. U and V both have this property that UI dot product with UI is equal to 1, and UI dot product with UJ is equal to 0 when I is not equal to J. So if you take one column vector dot product with itself, you get 1, meaning that its L2 norm is 1, if you think back to when we talked about norms, or its length is 1. And if you take any other column vector and dot product it with any other column vector, you get 0, meaning that all columns are orthogonal to one another. And so these two things together mean that they're orthonormal. And so we say the columns of U and columns of V form an orthonormal set. I can't spell normal set. Well, okay, great. Again, who cares? Well, mathematically, we can express this sort of statement as being a single matrix multiplication. U transpose U is what we call an inner product matrix. It consists of all of the sort of dot products of all of the columns in U with all of the other columns in U. And so I'm not going to sort of work out the details right now because this was covered in lecture, but a result of that is when you multiply U transpose by U, you get back the identity matrix. And when you multiply V transpose with V, you also get back the identity matrix. Question, do these two identity matrices have the same dimensions? Yes or no? What is the dimensions of this identity matrix? And remember, the identity matrix is a matrix that's diagonal with 1s on the diagonal and 0s everywhere else. Do they have the same dimensions? So we have a yes. Any other answers? Okay, another yes. Great. The answer is yes. And the reason for that is because since U is n by D, U transpose is D by n. And so the inner n's cancel out. So the result is that you have a D by D identity matrix in both cases. But then again, you'll be like, what is the point of all of this random math? Well, now we finally have enough to actually explain where principal components come in. So let's go back to the singular value decomposition. We can use the fact that V transpose V is the identity to sort of multiply both sides of this equation by V, giving us that X times V is equal to U times sigma. And now these matrices, they're matrices, but they're also products of other matrices, define what our principal components are. And so I will walk through interpreting what the product of X and V is, just because I think it's a little easier to sort of wrap your head around. But an important takeaway I want you to have is that anything that you can do with X times V, you can also do with U times sigma and vice versa, because they're equal. Okay, any questions with the singular value decomposition so far? Any questions? Okay, so let's go back to this weird example where I have some matrix where the columns are, I don't know, age, height, weight, GPA, number of siblings, whatever. And let's just say this is our X that we've already mean centered. Let's say our V matrix looks something like this. I don't know, 2, for concreteness, let's just say we have 5 columns in our X matrix. We have 2, 3, 1, minus 4, 1, and minus 3, 2, 0, 1, minus 2, and so on and so forth. The first principal component of my data is the first column of this matrix multiplication. But the first column of this matrix multiplication is just the result of multiplying my design matrix X with the first column of V. And the result I get is the dot product of, the first column of V and, my features. So I get like 2 times age plus 3 times height plus 1 times weight plus minus 4 times GPA plus 1 times the number of siblings. And this is all a principal component is. It's a linear combination of the features in my design matrix. The singular value decomposition tells us what the weights of our linear combination should be, such that variances are maximized, such that our principal components maximize sort of explainability in our underlying data set. And so that's all a principal component is. The second principal component would be the result of taking my design matrix and multiplying it by the second column of V, which would then be, this one. And so on and so forth. And so the reason I give you this weird example is because we can interpret V as containing the directions of our principal components. This first column here that I've highlighted in yellow defines the direction of our first principal component, because those are the weights that we apply to the columns of our design matrix to convert from raw features to the first principal component. The column highlighted in red is the direction vector for the second principal component, and so on and so forth. Now, can anyone point out a flaw in the example numbers that I've happened to draw for the first and second columns of V? So like, the big picture idea is fine, but there's something not quite right here. What is that? Okay, so one answer is that you can't have negative age, and we will address that momentarily. Are there other potential flaws with my yellow and red columns that I've drawn?
Hint, think about the properties of the V matrix.
Yeah. Yeah. Okay, so we established earlier that the columns of U and the columns of V both form an orthonormal set. I only wrote the properties for U, but they also apply for V. Meaning that the dot product of any column with itself should be 1, and the dot product of any column with any other column should be 0. But here, if you were to take the dot, if you were to take the dot product of this yellow column with itself, you'd get, I don't know what you'd get, but it's not 1. And if you take the dot product with the yellow column with the red column, you get, something else that's definitely not 0. And so an important fact of the direction vectors for principal component analysis is that they are orthogonal to one another. And I won't go through the interpretation of looking at a scatter plot and saying, oh, this is the direction of our first principal component, and this is the direction of our second principal component, because that's something we looked at in lecture and in discussion. But I want you to keep that in mind. This is like a purely illustrative example and not one that would mathematically actually work. Okay, great. So V contains the directions of our principal components. Some other terminology that's used for it is that it is the loadings matrix, or like it's the instruction matrix. Like it tells you, here's my data, here's how you convert to principal components. Great. Now, before we get to the part that we call Alan's cheat sheet, let's talk about the sigma matrix. Okay, we said it has D rows and D columns. And the elements on the diagonal are what we call the singular values of our design matrix. So sigma I is the singular value. Now, a linear algebra fact is that the singular values of x are the square roots of the eigenvalues of x transpose x. Now, we intentionally don't use the term eigenvalue at really any point in this class, although like that's an intentional decision. We could have used it at many points, like for example, when talking about regularization. So you don't actually need to know what an eigenvalue is in this class. But if you do, and you're supposed to because linear algebra is a correct, that's essentially all singular values are. Now, I have a question that I want to ask you if you have taken a linear algebra class. What are the eigenvalues of our design matrix X? So for an arbitrary design matrix, what are its eigenvalues? It's a trick question. Eigenvalues are only defined for square matrices, but almost always our design matrix is not square. Right? Almost always we have way more rows than we have columns. Like n is typically much larger than d. And so it doesn't make sense to think about an eigenvalue of our design matrix. Singular values, though, exist for any matrix because x transpose x is always square, regardless of the dimensions of x. So trick question, but anyways. Back to principal component analysis. What do these singular values actually mean? Well, they tell us the amount of variance accounted for by each of our principal components. And so the variance of principal component I, this is a definition, is equal to the ith singular value squared divided by the number of rows in our design matrix. A proof of this is in discussion. We really don't have the time to talk about it right now, but the discussion solutions walk through it pretty elegantly. Okay, so any questions with sort of the results of the singular value decomposition and how we use them to come up with principal components? So the singular value is not SD. What do you mean by SD? Standard deviation. Great question. No, these have nothing to do. I shouldn't say that they have nothing to do, but they're not directly related to standard deviation. No. In some weird formulations of, not weird, but in other formulations of the SVD, where you like divide by the square root of the number of observations at the beginning, then it happens to be the case that you can interpret it like that. But for our purposes, these sigmas is not standard deviation I. Great question. Yeah. Again, saying that it has nothing to do with standard deviation is misleading, but it's not directly related to standard deviation. Are we looking at the centered data when we take its length? Yeah, as you said, when we center our data, it doesn't change the dimensions of it. It just changes what the values in the individual columns are. But typically, right, like if you look at the lecture code, we will say, D is equal to X minus NP dot mean X axis equals 0. You don't, like when you're computing the variance of some principal component, like on homework 8 or whatever, it doesn't matter if you divide by the length of D or the length of X, because they're the same as you said. Does not matter. Cool. Okay, so with that, I want to move on to this last part, which again, we will call Alan's PCA cheat sheet because I stole it from him.
Doesn't contain everything you need to know about PCA, disclaimer.
Yeah, this is not, this is not comprehensive, but it should help regardless. So the first thing is, how do we compute the ith principal component? Everything I'm about to write is equal to the ith principal component. Well, we can take the ith column of X times V. We could also take the ith column of U times sigma. We could also just take X times the first column, or X times the ith column of V on its own. And by the properties of matrix multiplication, it's the same thing. Or we could just take sigma I multiplied by ui. And again, in discussion, it reasons a little bit more about why these things are the same. But yeah. These are all the ith principal component. The direction of the ith principal component is what? It's the ith column of V, which is equivalently VI. If you think of the subscript on V as being, which column we're indexing into. Now here's one that we didn't explicitly talk about. What is the rank of X? We didn't talk about this yet today. What is the rank of our design matrix? And sure, it is the number of linearly independent columns, but we didn't really talk about linearly independent columns here. So in terms of sort of some of the stuff that we have here, I'll leave it here as a hint. What is the rank of our design matrix? Is it the rank of V? You can get the rank of X by looking at S. So these ideas are close. They're all related, but yeah, great. The amount of non-zero diagonal terms in sigma indeed is the rank of our design matrix. And so, the length of the diagonal of sigma is D, right? But only R of those elements will be non-zero. The remaining D minus R of them will be 0. And so that's why here I've kind of written going from sigma 1 to sigma R, because everything else will be 0. Now, it's possible that they're all non-zero, meaning our design matrix was full rank, but generally that won't be the case. And so the rank of X is the number of non-zero. I shouldn't say generally that's not the case, but when looking at PCA, that happens to be the case quite a bit. Number of non-zero singular values, which is equal to the number of non-zero sigma i's. Great. Why exactly that's true? You might want to look at the dimensionality reduction lecture where we interpreted, or not interpreted, but where we came up with low rank approximations of our design matrix and sort of how we could use U sigma and VT to come up with low rank approximations. And the number of non-zero singular values is tied to that idea. But sort of if you just want to take it at face value, that's the rank of our design matrix. The variance explained by PCI, we already talked about this, that's sigma I squared over n. What's the proportion of variance? What is that? What is the proportion of variation explained by just principal component I? Any ideas? This is also something you explore in homework 8. Great. So it's the variance of just PCI divided by the total variance. So this is equal to the variance of PCI divided by the variance in total. The variance of PCI is sigma I squared over n. The total variation is, sigma 1 squared over n plus sigma 2 squared over n plus so on and so forth, all the way through sigma r squared over n, where r is the rank of our design matrix, because we assume all the other sigmas are 0. But the n's on the numerators and denominators can cancel out, and so we're left with sigma I squared divided by this sum, and I'll use a different index here, of the sum, or it's the sum of the squares of all singular values. So this is the proportion of variation explained by just PCI. So the proportion of variation explained by PC1 and PC2, well, you would just sum this quantity for both PC1 and PC2. If you sum it for all PCs, the result you get back is 1, because the proportion of variation explained by all principal components, well, is all the variation, which is just 1. Okay, I want to turn it over to Alan to talk about using PCA sort of in scikit-learn, which is not something we did in lecture. There was a little bit about multi-collinearity that I wanted to talk about, but I don't know if we have the time for that. But any questions about the sort of math behind PCA? One thing that I will write down, but not really talk about right now, there's a nice little sort of addition to the lecture slides about this, is that you can think of coming up with principal components as being two equivalent goals. One is that we want to capture as much variation in our original data as possible, but the other is we want to minimize projection error. And the thing we are projecting onto are the sort of directions defined by our principal component direction. So the columns of our V matrix, or equivalently the rows of V transpose. Cool. Okay, let me turn it over to Alan. Go for it.
Are you sure you want to? I think the multi-collinearity stuff is probably more important because it's more in scope.
Sure.
We
can go through that very quickly.
Yeah. Because the PCA for modeling stuff is kind of extra. It's not really in scope.
Sure. Okay. This will be relatively brief, and if we have the time, we will connect this back to PCA at the end. But let's sort of switch gears and go a lecture back and talk about multi-collinearity. Can someone remind me what multi-collinearity is? I forgot. Does anyone remember what it is? What is it? Great. So you're all almost there. The situation you described, where one feature is a linear combination of others, is multi-collinearity. but it's not necessary that one feature is exactly a linear combination of others for there to be multicollinearity. Multicollinearity, more generally, is just when one feature can be explained like relatively accurately by a linear combination of other features. And another way of thinking about that is that one feature is correlated to some other feature. Great. So let's quickly look at the example from lecture. Again, I won't spend too much time on this because, again, directly from lecture. Here we looked at, again, the same MBA model where we had 5 features: field goals, field goal attempts, free throw percentage, three-point attempts, and assists. And we saw that the coefficient on the resulting linear model that tries to predict points for field goal attempts was 0.036. And so if we take a step back, field goal attempts is the number of times a player takes a shot, and points is, the number of times they score. So we would think that the number of times a player takes a shot impacts the number of points they score quite a bit. And the coefficient here doesn't seem to imply that, right? Because the coefficient on the number of shots they take is 0.036, which is relatively small. And so we, as we saw in lecture, the issue is that there was multicollinearity, and it's because field goals, so the number of shots that they actually that went in, and the number of shots that they take is very highly correlated with one another, or are very highly correlated with one another. Right? The correlation between these two things is 0.97, meaning that field goal attempts can be predicted very accurately just using field goals. And so as a result, the coefficients in our linear model aren't necessarily meaningful. The point that I want to bring up here, though, is that multicollinearity is generally an issue when you care about the interpretability of your model's coefficients. It doesn't really impact the predictive capability of your model. Now, of course, here we don't have perfect multicollinearity. Like, it's not that one of these columns is a linear combination of other ones. So we can find a unique value for our optimal parameter vector theta. It's just that the elements in our theta vector don't necessarily mean anything. But we can still make accurate predictions. So if we don't really care about what the coefficients of our model are, and we don't have perfect multicollinearity, generally you can just ignore this and go on about your day. But if you care about the coefficients of your model, then you want to try and avoid multicollinearity. And so in here, there's a little demonstration where we look at the training and testing error for both a model with and without multicollinearity. So, first we fit a model, we can just do it real quick. First, we fit a model that just uses field goal attempts as its sole feature plus an intercept term. So there's no multicollinearity because there's only one feature. Its coefficient is relatively large, and you can see its RMSE on test data, because I did a train test split, is 1.04. Now, without context, that doesn't really mean anything. But what I will now do is fit a model where there's clearly multicollinearity at play, because I'm using just field goals and field goal attempts. I can't say the word goal for the life of me. If you watch the lecture videos, I say it wrong every time. Anyways, we're fitting a model with just these two features. And as we established earlier, these two columns are highly correlated with one another, but you will see that the testing RMSE isn't really impacted by that. In fact, the testing RMSE is significantly lower for the model with multicollinearity. So the only point of this little demonstration is that multicollinearity is more about the interpretability of our model's coefficients and less about how well can we make accurate predictions. Okay, but as I mentioned, that was kind of an aside. One method for dealing with multicollinearity, as we saw, is just looking at the features, seeing which ones are correlated with one another, and sort of getting rid of one of the correlated features, which is what we did in lecture, right? These two things are highly correlated with one another, so get rid of one of them. But as it turns out, using PCA is another, technique that we can sort of employ to get rid of multicollinearity. And I'll let Alan show that off real quick.
Yeah, it's gonna be super quick. And again, this is pretty much not in scope.
But it is
This
really
stuff.
and
It's
it sort of
interesting, but
explains
not in
how you
scope.
use PCA
Yeah.
in reality.
Okay, so here I'm just like fitting the linear regression model with like all these features, and I get a RMSE of 0.56. So we can use PCA here. I choose 4 components here, but I think you can like play around with that and see like what works best. So this is like some syntax you haven't seen before. So this is like the scikit-learn implementation of PCA. It's not really the same as linear regression, logistic regression, or like decision trees, or even like k-means, but it's kind of similar. So what you can do is make this PCA object, pass in however many components you want, and then fit it, which kind of doesn't really make sense, but it's just called fit on your training data, and then call this function called transform on your training data afterwards. And this will give me the principal components. I can also look at the directions of the principal components using dot components underscore.
Which
So
is
this gives me,
misleading in the terminology that we used, because
Yeah.
we said like what is on screen right now is the elements of our V
yeah,
Yeah.
yeah. So this would be like V1, this would be like V2, this would be like V3, this would be like V4. This would be like your U sigma or your XV. And we'll see that here. I can compare this to the output of the SVD. If I just like did this and like subtracted the mean and did the SVD. So we'll see that these are basically the same. Like this first row of V transpose is the same as the first principal. The direction of the first principal component here. And similarly, like the second one is the same. I can also find the principal components themselves, and this will give me the same thing as this. So this is like negative 3.407, 3.68. This is also negative 3.407, 3.68. So this is just like an alternative way to do this. Instead of having to go through all this machinery of like centering and calling MPNL, now like the SVD, you can do this.
One thing I wanted to point out, I honestly can't remember if I mentioned this earlier, but I meant to. We use the singular value decomposition to do PCA, but there are other ways to do PCA. So like the other big way to do PCA is by looking at the eigen decomposition of what's called a correlation matrix. Now, none of that really means anything for our purposes, but the reason I bring that up is because you can do PCA in ways other than looking at the singular value decomposition, just for your knowledge.
Yeah. Phosphide training. Okay. Yeah. So you can do the SVD, or you can use like the PCA object. And we don't use the PCA object in this class, but maybe in the future we will. Who knows? So what we can do is train a linear model with the principal components as the features. So what I can do is do that. I get some coefficients. One interesting thing is now what I can do is do PCA on the test data. And you might think like, oh, what if shouldn't I just be like doing PCA separately on the test data? But the like general consensus is that what you should do is do PCA on the training data, get your like mean and your principal components and everything from your training data, but then use those principal component or directions of your principal components as for your test data. So you don't project your test data onto the principal onto the directions of the principal components for the test data, but rather you do it for the training data. And that's kind of a very complex topic that we pretty much never talked about. So you have to know about that. But if you do homework 9, question 3D has a very similar concept, where basically what you should do is do PCA on your test data based off of the results of your training data, essentially. Again, the details of that is kind of outside of the scope of this class. We never talked about that. But here I'm using PCA model, which was fitted on the training data. But I call dot transform of this on the test data. So I'm transforming the test data into the principal components based off of the directions that we got from the training data. So what we can do is then fit a linear model on the principal components themselves. And we see that the RMC is 0.563. I don't know how that compares to this. It's slightly lower, but that just happened. That could have just happened by chance. Like if I did this again, this might have been higher or whatever. But basically the idea is that we can use the principal components as our features. And this is something called like principal component regression, or like a variant of it that, again, we didn't really go over in this class. But using that can help resolve, or like help ameliorate, is that the right term? the issue. Basically help improve the multicollinearity issue we had earlier, because once we decrease the dimension of our data, we don't have the multicollinearity issue as present as before. Sir, do you want to add anything?
Not really.
All right.
Just one last thing. Make sure to not confuse V with V transpose, because I see students making this mistake a lot. To get your principal components, it's X times V, but the result of the SVD is U sigma and V transpose. So just make sure you know where you're looking. The principal component directions are the rows of V transpose, but the columns of V. So just keep that in mind. There's a question in here.
Principal component regression would help reduce overfitting. Yeah, that's basically the idea. It can help reduce overfitting, but might not necessarily in all cases. Because in general, like if you reduce the dimension of your data, then you have a less complex model.
Cool. I'll stop recording here.